Hello everyone, Michael here. This is part 6 of my OpenLAP series. In part 5, we talked about straight line simulation in OpenDRAG. And we finally made it. Today we are going to take a look at lap time simulation in OpenLAP. As always, I suggest you download OpenLAP and follow along. So first of all, we need two things to run a lap time simulation. We need a vehicle from OpenVEHICLE, we need a track from OpenTRACK, and these two things are fed into OpenLAP that drives the vehicle around the specified track. What OpenLAP generates for you after all the computations is three things. Firstly, it creates MATLAB plots with the results and saves those results in a .mat file. This MATLAB plot looks something like this, with the velocity, the elevation, the curvature, the accelerations, the driver inputs, and the steering wheel angle and wheel angles in the top 5 graphs, the GGV plot on the lower left, and a track map colored by velocity. Now inside the .mat file you will find three structures. The first one includes the vehicle info, the second one includes the track info, and the third and last one includes the simulation results, again in a structure format, so that the units are included as well. So if you click, for example, in the speed structure, you're going to have the units in meters per second and the data in a vector. Secondly, it creates a log file that includes the same information that is included in the command window, but also includes a table with all the calculation steps. This here is an example log file. You can see that it includes basic info, some status updates in the beginning and in the end, and it also includes a table with all the velocity computations. Thirdly, it exports a CSV file that includes the data from the final solution. As you can see, the format resembles the one used by widely used data analysis tools. When you press the Run button, what happens is that OpenLAP reads the specified vehicle and track files as well as the user settings. Then it starts the simulation and calculates the maximum speed trace for the pure lateral condition. Then it goes on to calculate the real apex positions. We will see in a bit why it has to be done this way. Then it sorts the apexes from slowest to fastest. As we saw in part 2 of the series, we do this because it allows us to do as few calculations as possible without wasting resources solving for velocity values that are going to be omitted in the future. Then it accelerates the vehicle from all the apexes. After, it decelerates it, and then it post-processes the results. Finally, it saves the results, creates plots, and generates a CSV report. As you can see, it is basically the same workflow as the one shown in part 2 of the series when we talked about the lap time simulation algorithm in general. But there is one main difference. As you can see, to find the apexes, OpenLAP calculates first the maximum speed trace for the pure lateral condition. Let's see why this is the case. Let's look at the Michigan International Speedway. Here we basically have a straight colored in green, two left turns colored in red, and one very large radius turn that passes through the start-finish line colored in blue. If we looked at the turning radius plot for this track, then conventionally we would say that the apexes would be located at the local minima. This means that we would find these two blue points, and then we would calculate the speed trace. But what happens in a dry race when a car blows its radiator and pours coolant all over the start-finish line? Well, then the cars on slick rubber would have to brake and drive through the wet surface slowly to not overshoot and hit the wall. This means that the velocity trace would be modified and look something like this. And this illustrates the problem I'm trying to explain very well, as a new apex appears out of nowhere on the start-finish line even though there are no curvature local extrema at that point. So there is something more to this. Okay, so how do we find the apexes? Well, if we look at its definition, an apex appears whenever a vehicle has just stopped accelerating, is at a pure lateral condition, and will start accelerating right after. This can happen whenever we have a local maxima in the curvature, a local minima in the grip factor, and a change in banking or slope. And the only way we can find one is by looking at how our vehicle model responds to all of these environmental inputs in terms of its maximum velocity value. And this value comes out of the pure lateral condition, i.e. when the tires are only used for lateral force generation. On the right, you can see a plot that shows the maximum velocity trace in blue and its local minima circled in black. You can also see the final solution in orange. What comes into play here is the vehicle's inability to use all its lateral performance everywhere. And what the driver tries to do is move this arbitrary green speed curve upwards. You can think of this speed trace as a rope that is allowed to touch and wrap around bumps created by the blue curves, but is not allowed to move them. This will make it hang in mid-air between the bumps in a sense, showing us the vehicle's combined performance. What the engineers try to do is move the blue curves upwards and make the rope more flexible, increasing the area underneath it and subsequently the vehicle's performance. To get the maximum velocity trace, OpenLAP uses its vehicle model lat function. This function looks at each point on the track independently and calculates the maximum allowed speed. While on a straight, it just chooses the engine limiting speed. While cornering, this function first calculates the red point, which is the maximum lateral force point. Then it corrects the solution and calculates the green point, which is the pure lateral condition. Let's now see how we get the maximum lateral condition. We take the equations we showed in part 3, we combine them, and then we plug them into the lateral force equilibrium equation. We have all the forces on the left side, and on the right we have the desired output, which is the pure circular component. When you do this, you get a fourth degree polynomial in terms of speed. But as you can see, you get the fourth and the second power of speed. This means that it effectively is a quadratic formula where you directly solve for the speed squared. These are the coefficients. I am obviously not going to go through the process of the algebraic manipulation, but you can try it out yourself if you want. When we set this equation up, we get 4 solutions if a is not 0 and 1 if a is 0. We obviously choose the positive so that the square root can give us real numbers. The speed we have just calculated is a speed that effectively provides enough downforce to negotiate the turn, but the drag does not allow for this value to be maintained. Also, because we use the maximum value for the lateral force, there is no available longitudinal tire force to combat this net drag. So we need to reduce it by a small amount so that the friction ellipse will allow some longitudinal force to exist and at the same time reduce the drag by a small amount. Let's now correct our first estimation. We have obtained our velocity value. Now we can calculate all the external forces like aero, rolling resistance, and so on. Having those values allows us to find what the maximum lateral tire force is. We can now also get the needed lateral acceleration to negotiate the turn, taking banking into account. Then we set the longitudinal force to be the opposite of the sum of all the rest of the longitudinal forces. This is so that the net longitudinal force is 0 in the end. With the longitudinal force now known, we can calculate the remaining lateral acceleration from the tires. And now we compare the remaining lateral acceleration to the needed lateral acceleration. In our first iteration, this comparison will probably give us a value under 1 as we have less lateral than we need. When that happens, we calculate a new value for the speed using the remaining lateral acceleration. And we use this new velocity value and start the loop again. If the fraction returned a value that is over or equal to 1, then it would mean that we have more or barely enough lateral acceleration remaining to negotiate the turn. Let's now look at the function in the code. So as you can see, this function takes in the vehicle structure, the track structure, and the current point index, and gives us the velocity value, the throttle position sensor, and the brake pressure sensor values. In the beginning, we get the track data. Keep in mind that this is the total grip factor from the vehicle and from the track itself. Then we get the vehicle factors and the number of driven wheels, the mass, the normal load on all the wheels, the induced weight from banking and inclination. Now to solve for the speed, first we check if we are in the straight by checking if the current curvature is 0. If it is, then we just get the maximum value and we set the throttle to 1 and the pressure to 0. Otherwise, we are in a turn. So we calculate a D parameter, we get the tire lateral and longitudinal coefficients, and here we define the quadratic formula coefficients. If A is 0, we have this solution. Otherwise, we just search for the positive solutions so that we actually can use the square root function. Obviously, if we land here or here, then we have problems. With that done, we just choose the minimum value between the solution, the maximum allowed by the engine speed, then we set the speed correction flag to true and we initiate an infinite while loop. In this loop, we calculate the aero forces, the rolling resistance, the driven wheel load, the drag longitudinal acceleration, the maximum allowed by the tires lateral acceleration, and our needed lateral acceleration. And then we check if the longitudinal drag acceleration is less or equal than 0. If this is true, then we need to apply throttle to compensate for that. If this isn't true, then we need to apply brakes to compensate for that. Obviously, in this if statement, we get the maximum longitudinal tire acceleration, the power limited acceleration, we get the remaining lateral acceleration from the tires, the longitudinal acceleration available by the tires, and we calculate our throttle and brake inputs. The same applies for the brake condition. Here we actually check if we have enough grip to negotiate the turn. If we don't have enough grip, we update our velocity estimation, and if we have enough grip, we set the speed correction flag to false. This effectively breaks the infinite while loop we have started here. All this is done to effectively solve this full equation. This is also a polynomial of the velocity variable. But when you start plugging in the values for everything, then you will see that it becomes a 12th degree polynomial, or at least I think it's a 12th degree one. When I first came up with this equation, I was faced with hard truth that even for the simplest models, this problem becomes complex enough that you need numerical methods to solve it. So this is why I use the method I just described to find the pure lateral condition and don't solve an equation directly. The idea is that I omit the ellipse factor, which is basically the square root in the beginning, making this a solvable polynomial that I use to get the first estimation of the final solution. In my experience, this makes the correction loop run between 3 to 5 times before an acceptable value is found. I am aware of the fact that this method might underpredict the value by a very small amount. I am also aware that you could code in a bisection or Newton-Raphson solver to solve this big equation in one go. But again, this would need 1 or 2 guesses to start with and then some more iterations on top of that. So I did not feel the need to make the effort to optimize this process as it was fast enough for me. As an example, I have here a graph of our generic F1 car around Spa. You can see the maximum speed trace in blue, the apex speeds circled in black, and the final solution in orange. Again, you can look at the orange curve as being a rope hugging the blue maximum speed curve peaks and hanging in between them. Okay, so we saw how we calculate the maximum speed trace, and that we take the local minima of this trace to find the apexes. But as I said in slide 5, we know that an apex will appear due to curvature and grip factor local extrema or changes in the banking or slope of the circuit. But why do we go on and calculate the maximum speed trace in all the nodes of the track? Why not only search for those points that might create apexes and only solve those? Well, because we also use the maximum speed trace for overshoot checks. Let's look at this graph to explain what I mean by this. We have this maximum speed trace. The apex is at the minimum, so we start accelerating from there. We calculate one step and another one, and we have gained this short curve. At this point, the mesh size or the distance to the next node is dx. If the vehicle has enough power and grip, because of the constant acceleration between the nodes assumption in the solver, we might get a velocity value that is more than the maximum or the one that the blue curve actually allows. This means that we have to constrain the solver to not apply all the available longitudinal acceleration potential. If we do this correctly, then we will land exactly on the blue curve as shown by the green point and curve. After this, we can continue accelerating normally. And this is why we calculate the maximum speed trace on all the nodes, to free ourselves from the need of calculating multiple future checks for overshoot. We just look at the maximum speed trace and find our local maximum allowed acceleration value. For the acceleration and the deceleration sequence, OpenLAP uses the vehicle model comb function. This function calculates the combined characteristics of the vehicle and connects the points by taking into account the vehicle's performance envelope and the limitations imposed by the track. This is basically the function that, in a sense, uses the GGV diagram. To do this, this function takes the current vehicle state as an input. Then it goes through and calculates the external forces, the drag acceleration, and the track overshoot acceleration. The mode variable is either 1 when in acceleration mode or -1 in deceleration mode. Then we find the currently used lateral acceleration and the tire maximum lateral acceleration. Then using the ellipse equation, we calculate the longitudinal modifier. Then we calculate the needed acceleration to barely hit the Vmax curve. Keep in mind that drag is a negative number, so minus something negative becomes positive. Then we come to an important step. Here we check if the needed acceleration is positive or negative. If it is positive, we need to apply throttle. If it is negative, we need to apply brakes. When applying throttle, the remaining tire acceleration is found by using the ellipse modifier and the driven wheel normal load. Then the engine maximum acceleration is found by the torque curve interpolation at the current speed. After, the throttle position is calculated by getting the minimum between the needed acceleration and the remaining tire acceleration. Then we divide this number by the engine maximum acceleration. This gives us a positive number that is less than 1 when we have more power than grip or we may overshoot, and more than 1 when we don't have enough power to saturate the tires or to overshoot the next point. When this happens, we obviously constrain the TPS value to 1. Finally, we get the commanded by the driver acceleration. Now, if we need brakes, we first get the remaining longitudinal acceleration, calculate the braking pressure using the Vita parameter from the vehicle model, and find the commanded by the driver longitudinal acceleration. Note 2 things here. First, the braking pressure does not drive the vehicle's response, but is driven by it. And second, we assume that the driver can apply as much braking pressure as the vehicle needs. Having found the commanded acceleration, we calculate the final value of the longitudinal acceleration and the next node speed. Again, we utilize the mode variable to correct for the sign of AX in the formula. This is done because in deceleration mode, we will have a negative value for the acceleration. But because the car is moving rearwards, the next speed needs to be higher, so we need to remove that negative sign. Finally, we check if the speed we just calculated is less or equal to the maximum speed allowed on the next point. If it is not, then we have overshot the next point, so we stop the calculations and move to the next apex to save CPU time. If it is, we have successfully gotten an acceptable new state and we move on to the next point inside the same apex iteration. Then the flags are updated and the loop starts all over again for the next point. The most important thing to note here is that the mode does not necessarily define the application of throttle or brake. Think of a steep downhill. You might be just touching the brakes to adjust your speed, but you may well be accelerating due to gravity. The same happens when you lift the throttle by some amount, but the drag is enough to slow you down. What matters is the final result of the vehicle as a whole, not what the controls inside it are doing. The controls are just there to make the vehicle accelerate by the required amount. I did make this mistake when I started coding my own simulators, and I always found myself chasing my tail. Let's now look at the code for this function. As you can see, this function takes in the vehicle structure, the track structure, the current speed, the maximum next speed, the current index, and the mode. And it gives us our maximum speed value at the next node, the longitudinal and the lateral accelerations, the throttle and brake pressure sensors, and our overshoot flag. We begin by setting our overshoot flag to false. We get the track data and the vehicle data. Then we get the mass and we calculate the normal load on all the wheels, the induced weights, the aero forces, the rolling resistance, the driven wheel normal load, the maximum overshooting longitudinal acceleration, the drag acceleration, and our needed acceleration. Then we get our current lateral acceleration, the lateral tire coefficients, the longitudinal tire coefficients, and then we check if we are actually using some lateral acceleration. If we are not, then the ellipse modifier immediately becomes 1. If we are using some lateral acceleration, then we get the maximum lateral acceleration from the tires. Just check if we already have overshot for some reason, this shouldn't actually happen, and then we calculate our ellipse modifier from the ellipse equation. With everything now known, we check if our needed longitudinal acceleration is a positive number. If it is, we need throttle. If it isn't, we need brakes. In here, when we have our throttle position and brake pressure sensor values, we can get the commanded acceleration by the driver. With this known, we get the final value of the longitudinal acceleration and our next point velocity. In case we hit the engine speed limiter on the straight, we just force the throttle value to be equal to 1, and we assume that the cut comes from the electronics and not the driver himself. Then we finally check if we have overshot the next point. If we have, we set the overshoot flag to true and we reset our values. Now, previously I talked about the flag. This flag is a table that allows us to keep track of which points we already have looked at. Combined with the velocity solution matrix, we can check the solver state and not do unnecessary calculations. These tables have both equal number of rows to the amount of nodes on the track. The flag table has 2 columns, one for acceleration and one for deceleration. And the velocity solution table has a number of columns that is equal to 2 times the number of apexes. For the flag table, we just use 2 columns because we do not need to keep track of the apex. Just the fact that we already have calculated this point in this mode. The checks the solver performs to see if it needs to stop the calculations and move on to the next apex is basically a check of the complete row. If the flag is 0 in both columns, then it passes the test automatically and moves on to the next point. If the flag has 1 in one of the modes, then the speed is checked with all the columns in the solution matrix. In the same mode, the speed needs to be higher or equal to the pre-calculated one to stop and move on to the next point, and in the other mode, the speed needs to be higher than the pre-calculated ones to stop and move on to the next apex. The reason I have used 2 columns for the flag is debugging. You can also make it work with only 1 column. Let's find those checks in the code now. In our main simulation loop, we see the use of the vehicle model combine function that gives us the velocity at our next position and our overshoot flags. If the overshoot is true, then we just break the loop. If it isn't, we check the current flag value. If it is 1, then we do the checks that we just talked about. This is the check in the same mode with the same k value, and this is the check for the other mode with a k rest value. If one of those 2 is true, then we just break the loop. Let's now look at the complete code to get a better picture of the whole process. First, we clear the memory. Then we start the timer. We select our track and vehicle files. We load those files. We set the export frequency. We add the current date and time in the file name if we want to. We update the heads-up display. And here we do our simulation. When we get our results, we display our lap time and we plot our results here. Here we save our figure and then we generate our report. So the main thing we need to look at is this simulate function. This is the first function that I've defined, and it takes in the vehicle structure, the track structure, the simulation name, and the log file ID, and it gives us our simulation results. In this function, we start the timer, we pre-allocate our maximum speed trace variables, and we calculate our maximum speed trace using the model lat function. Then we find those apexes, and we eject 1 extra apex in the beginning in case we have an open circuit, which actually forces the standing start in the beginning. If we haven't found any apexes until now, we just inject 1 randomly with one of our minimum Vmax values, and we create an apex table and we sort that table and get our final apex points and apex velocity points. We also get our throttle position and brake pressure sensor values at the apexes. Then we pre-allocate in memory our needed variables. We update the heads-up display, and we start our simulation. So we loop through all our apexes and all our modes. So K is 1 or 2, indicating that 1 is acceleration and 2 is deceleration, and the mode variable is either 1 or -1 for the correction inside the combine function that we talked previously. The K rest variable shows us the other modes. This check here just stops OpenLAP from running in deceleration mode at a standing start in an open track. When this is false, we get all the other apex numbers in a vector, we get the current index, we inject this pre-solved apex into our solution matrix, we update the flag, and we move on to the next point. If we are not in a standing start, then we assume that we have the exact same speed right after the apex, and we move on to the next point again. Here we start an infinite while loop. We use our combined vehicle model function to get our next state, we check for the overshoot, we check for any pre-solved cases, we update the flag, and we go to the next point. And here we check if for whatever reason we have completed a lap. And there are 2 cases, the closed track case and the open track case. In the closed track case, we just check if we ended up on the point that we actually started, and in the open track case, we check if we've made it to the end in acceleration mode or if we have made it to the start in deceleration mode. In case we've made it to the end in an open track, we update the flag before we break the loop. Now with the loop done, we update our heads-up display and we start our result post-processing. Here we get the final solution by getting the minimum value in each row of the velocity solution matrix, and we calculate the needed time between all the nodes, the sector times, and the final lap time. Then we calculate all the forces, the yaw rate, and we use the steering model to get the vehicle slip angle and the steering wheel angle. Then we calculate our engine metrics, some other KPIs, and we finally save all our results in this big sim structure. Okay, so we've made it. But was this all worth it? Let's run a simulation and compare the results to some real data. This is the only way we can answer this question. Okay, so first of all, let's see how OpenLAP Solver actually drives the vehicle. Here we see the results for our generic F1 car around Spa. The colored surface is the GGV map, and the red points are the operating conditions that OpenLAP has calculated. As you can see, those red points are situated right on the map. You can also see that some points are not located exactly on the map, and that's due to our GG circle movement, due to inclination and banking, as we saw in part 3. And this is because the GGV surface was calculated for 0 inclination and 0 banking. So the entry to turn 1 is pretty easy to spot because we brake in a straight line with all the acceleration potential that we have, and then we start sharing the longitudinal and lateral acceleration to drive the vehicle on the limit. Obviously, negative lateral acceleration means turning right in our case, so it makes sense that the points go down in speed, and then lateral acceleration is created, and then we turn to acceleration, where you can see that the speed increases again. Now obviously, this being a computer, it can actually drive the vehicle at its maximum potential every time, but in reality, a driver will always be inside the cone. The better the driver, the closer those red points come to the GGV surface. Let's now compare some data. Here we have a Lamborghini Super Trofeo car at Paul Ricard. This is just a random lap from the last test we did with a target racing team. In all the data that we're going to look at, red is real and white is simulated. Let's first look at the speed trace. Given the fact that this is just a point mass model and that the complete lap is solved in seconds, I would say the correlation is pretty good. I would say that the main differences are here in this region in the brakes for turn 1 and in this braking zone here. So the simulator brakes a bit later and a bit harder. And just for reference, the difference in distance and time is 45 meters in 0.6 seconds. In terms of gear selection, you will mainly see that the simulator actually uses mostly the same gears as the driver in reality, with the main differences being here in this region and here, where the simulator goes one gear lower. Although this might make sense in terms of torque delivery, we need to take into account the drivability of the car, meaning that sometimes it makes sense to stay one gear higher as the car is not that nervous. Also, you will see some weird downshifts here and here. These happen just because we only use an interpolation for the gear selection and we don't have a proper gear selection strategy implemented in OpenLAP. Also, we don't model the gear shift duration. So a selection of a gear for 1.2 seconds doesn't actually make sense in reality. In terms of RPM, it's better to look at this graph over here, where we actually have the RPM versus the corrected speed. Obviously, we have white points here in this region just because OpenLAP selects the first gear sometimes. But in general, the slope of each gear is correct. But you will also notice that as we go to higher speeds, it looks like the real car has a bit taller gearing. Although I have used the same exact gear ratios for the model, the thing that I keep constant but reality doesn't is the tire radius. So downforce and centrifugal forces due to the rotation actually change the diameter of the tire, and this is why such differences may appear. In terms of steering, although we are using a very simple steering model after the fact, we can again see that there is pretty good correlation, but sometimes the real car seems to be understeering, here and here for example. In terms of brake pressure, again we have similar results, but with differences in the braking points. In terms of general brake application, we see that OpenLAP starts with applying a high pressure and then bleeding the brakes off, modulating the brakes to the grip. In terms of throttle application, we can see that the white line has much more noise in it than the red line. Keep in mind that this car in reality has traction control. So basically what OpenLAP does is activate the traction control by itself. Also, the TPS map is not linear with power, but in OpenLAP it is. So you might see differences in the shape in general. The best correlation can be seen in the lateral acceleration graph. And this is to be expected because I used the lateral acceleration and the speed channels to actually create the curvature for this track file. In terms of longitudinal acceleration, we again see some pretty good correlation, with the largest differences again appearing at the braking points. Now, if we use the longitudinal and the lateral acceleration traces, we can plot the GG circle. So looking at the right, we will see that OpenLAP's GG circle is cleaner than the real one, but in general the shape is the same. Also here, plotting longitudinal acceleration versus speed, we can see that both for the positive side of the longitudinal acceleration and the negative side of the longitudinal acceleration, we kind of have the same shape, which means that the model is working correctly. Now here, where we have lateral acceleration versus speed, we have a symmetric plot, and again the general shape is the same, showing us that both the grip and the aero is working correctly for the model. Finally, down here we have the G-sum channel, which is calculated as the square root of the sum of the squares of the lateral and the longitudinal accelerations. It basically tells us what the GG circle radius is at every point. Now what we can see is that the basic shape is the same, but in this region here, 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 and here, we can see that OpenLAP fills up the small gaps, meaning that it is driving the vehicle closer to the edge while entering a corner. This might be something that the real driver can actually improve, but it also may be due to other reasons, like road bumps, changes in the car attitude that are not modeled in OpenLAP, and many other things. Again, the key thing to note is that although this is a point mass model, it comes remarkably close to reality. Let's look at something completely different now. This is a shifter kart in the KZ2 category. And this is a fast lap that my cousin did at Kartodrome Roads about a year ago. The first thing to note is that Mike did a 28.6 and OpenLAP did a 27.8. Now, I currently hold the lap record at this track and I've done a 27.9, which is remarkably close to what OpenLAP did, but keep in mind that usually simulations can show you laps that are 1 or even 2 seconds faster. So the absolute number of the lap time shouldn't be actually something you look at, but what simulation basically gives you is relative differences in lap time when you change something in the setup. And that's what you need to look at in general. Now, in terms of correlation, here the speed channel shows way more differences than it did in the Super Trofeo case, with the main differences being seen here in the GG circle. If you look at the braking deceleration that Mike can achieve, which is about 1G, while OpenLAP can actually brake with about 1.6 or 1.7. At the same time, in reality, 1.6 Gs are achievable while cornering. So this either means that karting tires can generate way more lateral grip than longitudinal, or that there is more braking potential to be found in the real kart. Either way, an inclusion of a braking pressure or a braking pedal force limit is an easy update to the code and will allow OpenLAP to simulate braking system limitations. Also, the drag that is induced when turning the steering wheel is not modeled in OpenLAP. And this is why, in the simulation, the kart can accelerate way more after turn 1 and is actually able to hit the speed limiter at the end of the straight. Again, the best correlation comes in terms of lateral acceleration, while there are more differences in the longitudinal acceleration channel. Now, due to this increase in braking potential that OpenLAP is actually using, it can actually brake about 12 meters or 0.4 seconds later. One key thing to note though is the correlation here in the entry of what we call the fig tree turn. This is a case of a turn that is wide in the beginning, and as you go on, it progressively becomes tighter and tighter. And you can see that OpenLAP can actually capture the performance of the kart in this region in a pretty good way. This is a lap that a Cranfield colleague of mine did around Laguna Seca in a Assetto Corsa with a mod car that lies between an F3 and an F4 car. The nice thing about this is that the vehicle model is way easier to create just because you can dig into the mod files and get all the values for all the variables that are needed, and then you can get results like this very easily and very quickly. In terms of speed, we see way better correlation than we did previously on the shifter kart, with the main differences appearing here in the entry for turn 5 and at the corkscrew. The corkscrew is actually a pretty interesting case, and this is because as the car comes up the hill, then the crest actually makes the ground disappear underneath the tires, reducing the normal load and subsequently the grip, which is something that OpenLAP cannot actually simulate. And this is why both in the braking zone and during cornering, we should see OpenLAP performing better. Again, gearing seems pretty similar, with larger differences appearing at larger gears and higher speeds as expected. We see similar steering traces, similar braking traces, although here and here OpenLAP brakes and the real driver doesn't. Also here and here, the real driver brakes earlier and less. Looking at the throttle, we see Assetto Corsa auto blipping during the downshifts, and as expected again, we see a noisier throttle signal from OpenLAP. Moving on to the lateral acceleration, we see the best correlation, with the main differences appearing at the corkscrew and right after. And in terms of longitudinal acceleration, we again see a very similar trace, with negative spikes appearing in Assetto Corsa due to the gear shifts, and some differences in the braking zones that actually follow the differences in braking application. Again, in the GSUM channel, we see that OpenLAP fills in some gaps. And finally, the GG circle looks pretty similar, and the long ACK and lat ACK versus speed graphs also look pretty similar to the Assetto Corsa data, showing us that the model is working correctly. Now again, in terms of lap time, OpenLAP is about 2 seconds quicker. And when I asked my colleague about this, he said that it is not unreasonable and that it should be doable. Now, wrapping up, I would like to say that I'm very pleased with the results that I'm seeing. And that's because this is a very simple model and it is actually able to be solved very fast. But keep in mind that it cannot give you everything. It does not replace full vehicle quasi-static simulations or transient simulations in any way. It's never going to replace those. But it doesn't mean that it is not a useful tool or that it cannot be used properly to actually gain a much better insight of what is going on. That's it for today. This video finally concludes my OpenLAP series. I hope you guys learned something and enjoyed this series as much as I did creating it. I have received quite a few questions about the series, OpenLAP's usage, and some of the concepts. So I'm thinking about making a Q&A video answering many of those questions and maybe going a bit deeper and explaining some things a bit better. This means that if you have any questions or comments, this is the perfect time to leave them below so that I can have a larger pool of questions to answer if and when I make this Q&A. Also, feel free to subscribe to my channel, like the videos, and share them with anyone you think might be interested. Thanks for watching, and I hope to see you next time. Enjoy OpenLAP.